is delivered by Sun. He's a first-year Doctor of Engineering student at Xiamen University. His research interests focus on computer networks. His work explores network protocols, network systems, discrete event simulation, and data plane verification. With that, I'll pass the time to Xun.
Okay, thank you. So good afternoon. I'll briefly present our work strand. It is a server-driven method for keeping mobile push connections alive without sending every maintenance packet across a wireless link. In short, a phone and server may retain a TCP connection or UDP connection or any kinds after Middlebox removes its mapping, NAT mapping. So client heartbeats prevent that failure, but each one can wake the radio of the device, so it's harmful for the battery time. And our work strand moves the maintenance to the server side and limits how far its packet travels. I will cover the problem mechanism and actual design and results of our work. So mobile push services depend on persistent connection that is active only occasionally. In deployment, that path contains many stateful devices. Like cellular traffic can cross carrier-grade NAT at packet gateway or use user plane function, while Wi-Fi traffic commonly crosses an enterprise or residential gateway. These devices, sometimes non-rigorously called NAT devices, maintain per-flow mappings and unfortunately removes idle entries to release ports and memory, and often too frequent from my ideal environment, therefore causing some problems. This removal is often silent, which means these gateways send their neither final or reset to the terminal devices, or there is no such thing for protocols like UDP or QUIC. And so the client and server retain established state, even through forwarding state no longer exists. When the server sends a push message, the gateway just directly drops it as there's no longer a valid destination information for it to anywhere. And no matter how much the server side tries, there's no way possible for the client to acknowledge this situation unless it actively tests the connection between itself and the push server. And recovery begins only after an endpoint detects failure and creates another connection. This requirement is therefore not just the socket at each endpoint. The middlebox mapping must remain present. Every middlebox must remain their state. So the mismatch persists because the endpoint lifetimes exceed gateway resource policies. So the response to this is this silent drop phenomenon is client-driven heartbeat. Its interval stays below the expected middlebox timeout, the lowest timeout throughout the whole chain. So each heartbeat crosses the path and refreshes the mapping. The payload may contain only few bytes, but payload size is not the main issue here, considering the device power consumption. On cellular networks, an outbound packet can move the modem from RRC idle into RRC connected state. This terminal exchanges control signaling and then remains a higher power state during an inactivity or tail interval. Measurements cited by the paper place this interval around 10 to 15 seconds in common LTE settings. A packet during the tail may add little, but an isolated heartbeat can cause the transition again. The result follows number and spacing of wake-ups more closely than payload bytes. Wi-Fi uses a different radio protocol, yet periodic traffic can still activate the device and interact with operating system batching. This coupling is the target of our work. Refreshing gateway state currently requires terminal activity. In power-critical applications, this behavior does hurt the usage time of some devices on a significant level. Therefore, we propose strand. A stateful gateway stores each flow as a 5-tuple mapping, often with a translated address and port. When the matching packet arrives, it finds the entry and refreshes its time before forwarding. Strand exploits this order. The packet only needs to reach the gateway, not the phone. The server creates this boundary using IP time to live. Suppose the phone is n downstream hops away. Strand sends a zero payload packet with TTL n-1 on the IP protocol layer. Each hop decrements the TTL. So at the final gateway, the packet matches the flow and refreshes the mapping, forwarding, then reduce the TTL to 0, dropping the packet before the wireless hop. The phone is not paged, the modem stays idle, and the application receives nothing. The packet is also injected outside the TCP retransmission queue of the server side. Otherwise, the missing ACK would trigger retransmissions or close the connection. So Strand must therefore learn to pass specific values. N, we have mentioned before, determines where the packet expires, and another time parameter, TMB, determines how long the mapping may remain idle. So how frequent should the server send a packet down the stream? Since timeout policies differ across gateways, a fixed interval is either unsafe for short timeouts or too frequent and costly for long ones. Strand obtains these parameters in 3 stages. During connection setup, the server observes an incoming packet TTL. Operating systems usually choose from a small set of individual values, so the difference gives an upstream hop estimate M. Because routes can be asymmetric, M only starts at the downstream search. The server sends probes with TTL values around M. Each uses a stale TCP sequence number. Under standard behavior, a probe reaching the terminal causes its kernel to return an ACK, while the application receives no data. The smallest TTL producing an ACK identifies N. N-1 is the truncation value. Separate timeout probing chooses an interval below the gateway threshold. After calibration, the server sends truncated packets on that schedule. A low-frequency end-to-end check remains necessary because these packets could preserve the gateway state after a phone disconnects. Failed checks let the server release a stale socket or restore client-driven maintenance. Route changes similarly trigger a recalibration or fallback, so no client modification is required. The second parameter, TMB, is costly to measure because the probe at time t requires an idle wait of t. Composite search, there's a existing method called composite search. It doubles the window until a probe fails, then applies binary search inside this interval. It limits probe count, but high-value probes still consume their full waiting time, so it's costly and it's not optimum. Strand has used a bounded discrete domain and assigns prior probability to timeout values observed in measurements. These values tend to cluster around configuration defaults for different routers or different switches, like 20 minutes or 30 minutes, and rather than from an arbitrary continuous distribution to increase the efficiency of the search. The dynamic programming algorithm chooses a monotonic sequence of probe boundaries. Its transition as prior cost, the next weighted by the probability of reaching it, and expected binary refinement cost if the true value lies inside the interval. Backtracking gives the schedule. This objective minimizes overall elapsed calibration time, rather than only minimizing the number of probes sent. Without a prior, it minimizes expected cost under a uniform distribution. With a prior set, boundaries move toward common timeouts, accepting added cost between them for lower expected cost, where probability is concentrated. The implementation is a hot pluggable Linux kernel module on the push server. kprobe and kretprobe plugs of the kernel module observe socket contexts and TCP IP functions. The push service does not need a new protocol or changed application logic. For probing and maintenance, the module constructs raw TCP packets from captured connection state, including the 5-tuple, sequence information, and TTL. Injection bypasses sequence accounting and retransmission queues, so an intentionally expired packet does not start TCP loss recovery. Calibration probes use a stale sequence number, so a conforming client kernel returns an ACK under RFC 9293 and discards the segment before application delivery. The architecture also provides rollback. Hooks can be unregistered and failed consistency checks can restore the client heartbeat. This matters because the gateway processing order and the router behavior are deployment assumptions, not properties shared by every device that follows the RFC regulation. The evaluation separates terminal energy from timeout search performance. The server module ran on a cloud push server with 4 phones of the same model. Each condition lasted 24 hours and was repeated 5 times. An airplane mode measurement of 347.5 milliamp hours was subtracted as background drain. On cellular access, native keep alives accounted for 287 milliamp hours compared with 171.4 on the strand, a reported reduction of 40.3%. On enterprise Wi-Fi, the values were 359.9 and 216.9 milliamp hours, or 39.7% drop. That Wi-Fi network used a 2-minute timeout versus about 20 minutes on cellular, so native heartbeats were more frequent. No connection error or missed push was observed throughout this process, although the tests covered limited phones and paths. Timeout simulation covered TCP values from 1 to 60 minutes and UDP values from 1 to 300 seconds. Unweighted DP dynamic programming algorithm reduced the average convergence time of the TMB search by 18% for TCP and 90% for UDP relative to composite search. At measured hotspots, weighted DP reported reductions of 28 and 26%. While some values between hotspots incurred extra cost. So to close, Strand moves state maintenance traffic and processing from phones to servers and gateways, so deployment must consider capacity and metering. It depends on Middlebox processing order and stable route boundary. Recalibration, end-to-end checks, and fallback remain necessary. IPv6 and deterministic port allocation may eventually reduce the net pressure behind the short timeouts, but for current paths, the main result is that a server can directly refresh a mapping without making each maintenance packet a mobile radio event. So